In this presentation we're going to introduce some of the signal properties. We're going to talk about the difference between finite and infinite length signals, learn what the periodic signals are, causal signals, learn how to decompose signals into their even and odd parts by exploiting symmetry. So let's start with finite versus infinite length signals. The length of a discrete time signal can be infinite or finite. An infinite length signal is defined for all time variables, and in the integers from negative infinity to plus infinity. So the right way to think of an infinite length signal is a signal with a time axis that basically flows all the way from minus infinity on one end to plus infinity on the other. And the signal takes its values for all values of n. Of course, infinite length signals are not practical, that is, cannot load them into a computer, for example. However, they are very useful conceptually, as we shall see. A finite length signal is much easier to think about. It's just a signal that's defined only for some finite range of the time variable. In this case, for example, from n1 equals minus 15 up to n2 equals plus 15. Very importantly, a finite length signal is undefined for values outside of this range n1 to n2. It's not zero, it is undefined and unknown. So that's finite versus infinite length signals. A periodic signal is an infinite length signal that repeats with a period that is an integer capital N. A periodic signal is basically as consisting of one fundamental period that repeats itself over time. And by looking at the definition here, the definition of a periodic signal is that if we take a particular value x of n at time point n, let's pick, for example n equals 5 in this case. Then, we have x of n or x at the time point of 5. So we can talk about x of 5. We can see that the signal takes exactly the same values at n equals 13 and n equals minus 3. And so basically we can see that x at point 5, x at point 13, and x at point minus 3. These are all equal to each other, and that's how we can work out that the period of this particular signal, that is, the period, n is equal to 8, so this is a periodic signal that repeats with period 8. Other two examples with period 11 are also shown, please see their periodicity. Importantly, the period has to be an integer, and if a signal is not periodic, we call it aperiodic. Periodic signal is very useful in infinite length signals. The last example is that of the radar signal, which is a linearly frequency modulated waveform and is sent by the radar repeatedly. Now, there's a number of different ways that we can convert between finite and infinite length signals. The way that we convert from infinite length signals to finite length is by an idea called windowing. And there are two ways that are used to convert finite length signals into infinite length signals. We can either zero pad the signal, or we can periodize. So let's talk about these key operations now. So windowing is basically the idea of creating a longer signal, or converting rather, a longer signal into a shorter signal. And it's a very, very simple idea. We basically place a window on top of our signal, and we select out just a chunk of that particular signal. So, we place a window on our signal, we ignore everything outside the window, and then we copy that window signal into a signal y of n. In this case, from n equals 0 up through n equals 5, 6, 7, 8, n equals 8. So the values of y of n are simply the values of x of n evaluated at this narrower range of the signal that we see when we look through the window at the signal. So, windowing's important. Another important operation is zero padding. This does exactly the opposite. It takes a short signal and it makes a longer signal. The basic idea here is to take a signal, for example, x of n that's defined between some n1 and n2. And basically, define an n0 and an n3 that live outside of these ranges and basically extend the signal outside the original range just by placing zeros into the signal. So mathematically we're saying that the zero pad of signal y equals the zero pad of signal x inside its range of definition. But then it equals 0 to the left of x of n and 0 to the right of x of n. So zero padding again takes a shorter signal and creates a longer signal. Periodization is another way to create a longer signal, or in fact, an infinite length signal out of a finite length signal. So periodization takes a finite length signal and creates an infinite length periodic signal. So it's a very interesting operation, and the basic idea is as follows. Say we're given a finite length signal x of n, and that signal x of n, right here, is of length capital N. In this case we can see that n equals 14. Then we can create the periodic signal y of n simply by the following formula that looks a little bit daunting, but it actually isn't. Basically what this says is create the signal y by taking the signal x of n and placing it in the signal y. That's exactly this fundamental period that we see here, this triangle. We place that inside here. And then take their signal and shift it to the right, this signal x. Then shift it to the right by exactly n samples. And then place it in the signal y, here. Shift it by minus n samples, which we see here. And then basically add up all of these copies of this shifted fundamental period, x of n, and you can see that what you will create, is a signal that is periodic with this exact same period, capital N. This long chain of sum can be expressed very succinctly as an infinite summation as follows. We basically say that the sampled values y of n, that is, the signal y of n, is the infinite sum over this variable m of the finite length signal x that is shifted by integer multiples of this period capital N. So this is where we get for m equals 0 we get x of n, m equals 1 is here, m equals 2 here, m equals minus 1, here, etc. So this is a very nice succinct formula for representing periodization. Clearly it should be now obvious if a single period of the periodic signal is given, or rather a finite length signal is given, then that finite length periodized signal carries exactly the same information as the periodic signal. Said another way, since a periodic signal just repeats the same fundamental period over and over, there is no additional information in a periodic signal than is there in the finite length signals that defines the fundamental period. And so, we are going to think interchangeably about finite length signals and periodic signals because we can go back and forth between the two. We go this direction by just windowing out one period without any loss of information. And we can go this way by periodization, again without creating or losing any additional information. So this is very useful, and we're going to see an application of this when we think about shifting finite length signals. So back to some more definitions. We say that a signal is causal if it takes a value 0 for all time indices that are negative. So causal signals are 0 for all time. And they take non-zero values here only for values of the time index that are bigger than 0. A signal is anti-causal if just the opposite is true. Basically, it takes values only for negative indices of time and for all positive indices of time, including the time point 0, the signal takes the value 0. And if the signal's neither causal nor anti-causal, we call it not causal or acausal signals. These are going to be important when we think about real-time signal processing systems. Next, it's very useful, especially once we start to talk about the frequency domain and Fourier analysis, to think about even and odd signals. These signals have a certain kind of symmetry and is important. Even signals are symmetrical around the time point n equals 0. What is mean by that is if we were to place a mirror at the time point n equals 0, we see that time signal is exactly reflected from the negative time axis onto the positive time axis. So mathematically, we say that a real signal x is even if x at minus n, for example minus 5 equals x at plus 5. You see these are equal. So this is an even signal. An odd signal also has symmetry, but now it kind of has a twofold symmetry. Firstly, if we put a mirror here at the time point n equals 0, an odd signal has a symmetry where we reflect over again. This is mirror axis, but then we have to flip the sign of the signal. So if we flip the signal, we would basically have the signal that's going negative here, flipping across the mirror. And then we have to flip across also the time axis. And mathematically, we say that a signal is odd, if the negative entries in this case, for example x of -8, equal the minus or the negated sign of the value x at the positive index, for example, x equals +8. So we have to multiply by -1 this value to get this value. This is very useful to think of even signals, and odd signals, because of a very handy fact, that every signal can be decomposed into the sum of its even part plus its odd part. And there's even a constructive way to do this. There's actually even a formula that given a signal x of n, we can create its even part via this formula. The signal e of n, the even part of x of n, is we just add their signal to the signal that has been time flipped, as we'll see with some pictures in a moment. And then we just normalize by dividing by 2. To create the odd part, we do almost the same thing. We take the signal, but instead of adding its time-flipped counterpart, we subtract its time-flipped counterpart. And again, we normalize. And the decomposition then just becomes any signal. It doesn't have to have any symmetry at all. X of n can be written as the sum of its even component, plus its odd component. And it's very easy to verify that this is true just using these formulas. So let's just verify that E of n, plus O of n, equals x of n. Well, from the definition of E of n, right here, and from the definition of O of n, we're basically just going to sum these two terms together. So let's start by pulling the signal values together, and pulling the 1/2s outside. So we basically have x of n, x of -n, x of n, and minus x of -n. And now you can see that basically these values cancel, because we're subtracting. We have 2, x of n divided by 2, which equals x of n. So we've just shown that the sum of the even and odd part equals the signal. Let's look in pictures at what this looks like. Here's a signal. The signal has no symmetry. It's neither even nor odd. But now let's compute its even part, its odd part, and verify that they sum up together to create the signal. So, let's create the even part of the signal. We take x of n, we time flip it, we basically run the time axis backwards, which basically flips the signal around the n equals 0 axis. Here's my x of -n, or the reflected signal. We're going to add this signal to this signal and divide by 2. And that creates this signal. And very interestingly, you can see that this signal in fact has even symmetry. Similarly, we'll take this exact same signal x of n and we will time flip it both around the n equals 0 axis and then basically negate its values. In this case, we're subtracting. And if you take this signal and subtract, you will generate this signal. And you can see that it is in fact an odd signal. Finally, if now we simply work vertically, taking this even signal, adding this odd signal, it's pretty easy to see that we, in fact, recover our original signal, x of n back that we started with. So, even part of a signal, plus the odd part equals the signal. It's going to be very useful later. So to summarize, we talked about classifying signals in different ways: real, infinite, finite length, causal, periodic, etc. And we came to a very important conclusion that the finite length signals are equivalent to periodic signals. So in the next few videos, we're going to use these properties in different ways to both understand signals and how they carry information and understand how to process them. Your support would be highly appreciated to like and subscribe to the channel.